Hi everyone, I'm Yuntao Wang from Tsinghua University. I introduce you FaceOri, a technique that can track head position and orientation using ultrasonic ranging on earphones. This work is a collaboration between Tsinghua University and the University of Washington. Earphones are one of the most ubiquitous accessories we use every day. We wear them around the house, at work, or on the go. With the earphones cord getting hot, the input microphone has migrated from a placement on the cable to a position at each of the user's ears. Well, most earphones leverage the microphone to take calls, and more recently to enable the active noise cancellation functionality. We found that this unique placement of these sensors can be used to unlock a broader range of context-aware interactions when the earphone is transformed into a spatial input device. This motivated us to develop FaceOri. FaceOri uses the speaker on any commodity device to generate an inaudible ultrasonic chirp, which is picked up by the set of microphones on the user's earphone, and then processed to calculate the user's face orientation and distance with respect to the device. We adopt the FMCW ultrasonic ranging as FaceOri's core method. Traditional FMCW radar uses linear frequency changing signal for distance measurement. This is accomplished by comparing the frequency of the received signal and the transmitted signal. The change of frequency is the time delay, also the distance the signal travels. However, there is the assumption that transmitter and the receiver share the same clock for time synchronization. Well, in our case, the speaker and the microphone are located at different devices. Their clock chips are not time synchronized. Therefore, we use the calibration procedure to solve this issue. Referring to Ultrasonic, we calibrated the clock by placing one microphone against the speaker for a couple of seconds. Therefore, FaceOri can establish a reference position and handle the continuously clock time drift between the transmitter and the receiver by applying a linear curve fitting solution. Since the microphones are located on the side of the head, minimal head shifts can cause the microphones to be oscillated from the speaker. This loss of line of sight significantly degrades the signal-to-noise ratio. These issues can significantly harm the tracking performance. Therefore, FaceOri adopts an inaudible triangular modulated chirp signal to reduce the Doppler effect. FaceOri uses a non-coherent integrated method with a safer adaptive thresholding algorithm for better SR. Once we obtain the three distances from the device to the three microphones, we can calculate the yaw and the pitch angle from the face to the device with the formulas listed on this slide. FaceOri also supports a binary attention classification method that detects whether the user is orientating to a device or not. This can still be useful in many scenarios. Different from the continued tracking functionality, this binary attention classification is calibration-free. To validate our method, we use the Galaxy S21 smartphone as the transmitter. The receiver includes an Ample H19 headphone, a Zoom H6 audio interface, and an MPU 9250 MU modular, and a ThinkPad X1 Carbon laptop as the signal processor. The MPU 9250 modular is used to compare the performance of a FaceOri to an MU-based solution and further explore a sensor fusion method. FaceOri software was implemented in Python with functions including streaming and logging raw audio signals, performing calibration, calculating orientation, and displaying the results. Lastly, we conducted a user study with 12 participants to evaluate FaceOri's performance in a three-dimensional space, with 3 different height levels and 9 grids in the 2D space. We used OptiTrack to provide the ground truth data. The result demonstrated that our system could achieve a dynamic tracking accuracy of 10.9 millimeters in the distance, 3.7 degrees in yaw, and 5.8 degrees in pitch. It can also determine whether one is looking at a particular device with a 93.5% accuracy. When compared with the existing MSW ultrasonic ranging solution, CAT, FaceOri achieved better tracking performance since it is more robust against the Doppler effect and the live side issues. When compared with the MU-based solution, FaceOri can achieve significantly better tracking performance in the yaw, but not the pitch angle. When compared with the RGBD-based solution, FaceOri is less accurate, but FaceOri has advantages in a wider field of view, perceiving visual privacy, and has the potential to support the interaction with the devices without cameras. Finally, we explored the possibility of a sensor fusion method by integrating FaceOri and the IMU. Therefore, we can track the yaw and pitch angles with higher accuracy than the IMU-based solution, but consumes less power than the SOR ultrasonic ranging-based solution. Our work can support a wide range of applications. FaceOri can capture activity or gesture input. For example, FaceOri can track and count users' exercise by continuously measuring the distance between the earbud and the smartwatch, enabling a more interactive exercise experience. FaceOri can make interactions more context-aware and intuitive. In the first example, the laptop locks and dims the screen when the user moves beyond a certain distance away from the device. In another example, the user is preoccupied and unable to provide touch input. When the user looks at the device, it can turn the screen and allow for the user to see their incoming messages. In this multi-device scenario, FaceOri can automatically pair the mouse and keyboard to the device that the user faces. To conclude, FaceOri has the following three main contributions. Firstly, we propose the spatial input technique that applies ultrasonic ranging to enable continuously head orientation and distance tracking using a built-in set of microphones in the commodity ANC earphone. Secondly, we implemented an end-to-end system, and the user evaluation demonstrates FaceOri's high dynamic performance in continuous tracking and binary attention detection. Thirdly, we explored the application space afforded by FaceOri with the prototypes of selected demonstrative experiences. We hope techniques like FaceOri can help to make our interaction experiences of the future more human-centered. Please read our paper for more details.